In this video, I'm going to talk to you about conducting a paired samples t-test using SPSS. With the paired samples t-test, the reason why you would conduct this particular type of test is when you have dependent observations between your population groups. So one of the most common applications of this test is when you have data that is collected over 2 time points. And commonly there's an intervention period as well. So this doesn't have to be utilized with intervention data. It can be utilized for other reasons too. But nevertheless, that's a common application. So to give you an illustration of what I'm talking about, imagine that I am a counseling researcher and I'm looking at change over time in response to a treatment on anxiety scores. So let's say clients come in day 1, they report on their levels of anxiety. I get an active treatment over, let's say, a 10-week period, and then measure them on anxiety at the conclusion of this treatment period. And I want to see if there are significant changes in the mean level of anxiety between time 1 and time 2. In that case, I could use the paired samples t-test to carry that analysis out. Or let's say that I'm running another study and I'm looking at the effects of statistics instruction on statistics knowledge. And let's say I measure students at the first day of class, which would be time 1, on their statistics knowledge, and then they go through the course, essentially a treatment period, and then I measure them on their statistics knowledge at time 2, which would be at post-test. So I might then again utilize the paired samples t-test. The key, one of the key things to note though is that if you're going to do any of these types of tests, the measurements themselves at time 1 and time 2, whatever they happen to be, need to be essentially the same. You don't want to have different measures or of different constructs and having different measurement scales associated with the different time points. So that needs to be constant because obviously if there are mean differences and you've used different measures, one potential problem is that, well, maybe you might be capturing different constructs. Measurements are oftentimes imperfect in terms of what they get at, so you could be tapping different constructs, or the scales themselves may be different. So trying to compare scales with different ranges on them would be like comparing apples and oranges. And the same would go if you have different constructs that are being measured. So the measurements need to be constant. So at any rate, I have a little set of data here. So I have, let's say I'm doing a counseling intervention. I'm looking at change over time and anxiety levels with the intervention period falling in between. And so I want to see if there are significant changes in the mean levels of anxiety from time 1 to time 2. And keep in mind too, just one other little footnote here, and that is that just because an intervention or a planned intervention falls in between the measurements at these different time points, doesn't mean that if I observe changes in the means, say from time 1 to time 2, that the intervention had anything to do with that. A change in means would be consistent with the effect of the intervention, but by the same token, without a comparison group, it really becomes or a control group, it becomes really difficult to make an unambiguous attribution of the changes in means to the treatment itself. It could be that there are other intervening factors that may have produced a change, and while the treatment was going on. So that's just a little footnote there to keep in mind, that that just because a treatment was enacted doesn't necessarily mean that the treatment necessarily had anything to do with the changes, although changes in the means would certainly be consistent with the treatment effect. So at any rate, I'm going to look at mean differences from time 1 to time 2 on anxiety scores. And when it comes to running these types of tests, we're running a t-test, a paired samples t-test. And when it comes to t-test, keep in mind that you have a basic null hypothesis. The null hypothesis is that the mean for the first group, in this case it would be pretest scores on anxiety, minus the mean for the second group, which are the post-test scores, is equal to 0. The alternative hypothesis, there are actually 3 possible alternative hypotheses, and they're broken out into what are called directional and non-directional hypotheses. A non-directional hypothesis would state mu1 minus mu2 is not equal to 0. And so this is a non-directional hypothesis, and what occurs is that you are carrying out essentially a two-tailed t-test. So you use a two-tailed t-test when you're testing a non-directional hypothesis. So basically what happens is that you start from the null hypothesis, which is no mean difference, and what we're trying to do is to determine if the difference we observe in means between the groups is far enough from the null hypothesis to conclude that that it's more likely that they represent different population groups. So what we do is we establish an alpha level, or which is our threshold for rejecting the null hypothesis. Conventionally, alpha is set at 0.05, but there might be reasons to increase or decrease alpha. And so what that means is that we are essentially drawing sort of a line in the sand in both tails of the sampling distribution for the difference in means. And what that translates into is that basically 5% of the sampling distribution is essentially being assigned to what's called the region of rejection. So in other words, this tail right here and this tail right here are referred to as the region of rejection. And that 5% is actually split into 2.5% in the upper tail and 2.5% in the lower tail. So if we observe a mean difference that takes us into this upper region or this lower region, then we would reject the null hypothesis. If the mean difference puts us here in between these regions, then we would maintain the null hypothesis. So the other possibility in terms of an alternative hypothesis is a directional hypothesis. And the directional hypothesis can be laid out in the following way. One possibility is we say mu1 minus mu2, or in this case it would be time 1 minus time 2 means, is greater than 0. And so in this case, if we're using the t distribution, it's very poorly drawn, but this is what we have in terms of our tools. So here's our null hypothesis falling right into the center of the sampling distribution. And our alpha level, our alpha is essentially, given that this is a greater than sign, we're essentially going to assign our region of rejection fully to the upper tail. So in other words, the entire 5% of the sampling distribution, if we set alpha at 0.05, is falling in the upper tail of this distribution. So what that means is that if we observe a mean difference between our groups that puts us up here, we would reject the null hypothesis, reject this right here, and adopt the alternative hypothesis. We would conclude that the population means are greater than 0. If what we observe in our data happens to put us down here, this is called the region of non-rejection, and in that particular case we would maintain the null hypothesis. A second possible alternative hypothesis is that that mu1 minus mu2 is less than 0. So this is another possible directional hypothesis. And in this particular case, our region of rejection would then fall in the lower tail of the sampling distribution. So there's our region of rejection. Here's our null hypothesis. So if the mean difference we observe in our sample puts us in this tail right here, we would reject the null hypothesis. We would reject this and adopt the adoptive alternative. If our mean difference puts us in this region right here, we would be maintaining the null hypothesis. So it was just a little bit of a refresher on the hypothesis testing procedure here, because we're using the t-distribution, and so we have essentially three different alternative hypotheses that we could adopt relative to the null hypothesis. I also want to point out too that when we're looking at our for the paired samples t-test, if we have an independent samples t-test, we would have an independent variable and a dependent variable. And so what we would have is we would have, let's say groups 1, 1, 1, 2, 2, 2, and then we would have our scores on the dependent measure right here. In the case of a paired samples t-test, we set up our data set a little differently. So the levels of the independent variable, which is actually referred to as a repeated factor, are indicated by two variables in the data set. And then so what we have are scores on the dependent variable at each level of the repeated factor. So the variables, I just named it anxiety time 1 and anxiety time 2. So basically these are scores on anxiety at each level of the repeated factor. So let's carry out the actual t-test. So let's say I'm just going to test a non-directional hypothesis, just that there will be a significant mean difference between groups. So I would go to Analyze, Compare Means, and Paired Samples t-test. And I'm going to reset this and show you how to do this. So we move anxiety at time 1 over, anxiety at time 2 over, and then we just click on OK. And so now you can see that we have our means for our two groups, so 6.5 and 4.5 for time 2. So if we take the difference in means, if we take anxiety at time 1 and subtract anxiety at time 2, the means, we get a mean difference of 2. And so you'll find this falling in this column right here for mean. And the reason why it says mean instead of mean difference is that technically speaking, if we were to go back into our data set and if we go back to our data set and not this data set, we go back to this data set right here, we could actually, if we take these scores right here at time 1 and subtract time 2, we would end up with a set of different scores. And essentially, if we take the mean of those different scores, the mean of those different scores is actually going to be equal to the mean difference. So that's why it says mean instead of mean difference. So you'll see that we have a t observed value, the degrees of freedom for the analysis, which is n-1 or sample size -1. And so the t value is just computed as the mean difference divided by the standard error of the mean difference. And so we end up with our t value here. So again, if we're testing a non-directional hypothesis, all we are concerned with is whether there is a difference in the means themselves. So we can utilize this value right here. This is called a p-value. And so essentially what we do is we compare the p-value against our alpha level. So if we set alpha at 0.05, we are comparing this value against 0.05. So conventionally, we would say if p is less than our alpha level, which less than or equal to our alpha level. So we'll just stick with the 0.05 level for this example. So 0.05, then we would reject the null, and we would conclude that there is a significant mean difference between groups when it comes to the dependent measure. So in this particular case right here, our p-value is 0.005. That's clearly less than 0.05. So we would reject the null, and we could infer that there is a significant difference in the means between the two groups. Now obviously, if I'm carrying out a treatment program and I'm looking to see if there are significant changes in means, ordinarily I would be, for anxiety, I would be looking to see if there's a significant decrease in the means. So, so in that case right there, I would have a directional hypothesis. And so my research hypothesis would actually be that mu1 minus mu2, or pretest scores minus post-test scores, is actually greater than 0, because I'm essentially would be hypothesizing that the anxiety levels would be higher at time 1 than at time 2. So what that means then in terms of my test is I need to look at down here at the mean difference. And, you know, I mean, I could visually just ascertain this right here, and clearly that happens to be the case. So the difference in means, which is 2, which is just computed by taking the mean of time 1 minus the mean for time 2, the difference in means is in the hypothesized direction, which is that it's positive. If it was actually negative, then really this no longer becomes a possibility, because that would mean that anxiety scores were actually higher at time 2 than at time 1. So if we happen to have a negative in this particular case right here, this would be not something we could adopt, and we would have to stick with the null hypothesis. But it actually turns out to be the case that our mean difference was positive, so that's consistent with our directional hypothesis. When we look over here in this for the p-value, we see that yes, it is less than alpha at 0.05, so we could reject the null hypothesis. I do want to make a little bit of a statement here, and that is that technically speaking, the p-value for a one-tailed test is half of this value. So, you know, technically the p-value is actually equal to 0.0025 as opposed to 0.005. But because we were able to reject the null with the two-tailed test, then we're good. But where this really matters the most is in those cases where you're testing a directional hypothesis, and let's say the p-value that is printed out in your output, let's say it was printed out as 0.06. So if you were comparing this against the alpha level set at 0.05, you would have to maintain the null hypothesis. But because the p-value for the two-tailed test is actually, for the one-tailed test is actually half of that for the two-tailed test, when the actual p-value for the one-tailed test is 0.03, and so when you compare that against the alpha level at 0.05, you'd be able to reject the null hypothesis. So that's why it's kind of important to understand that little detail. If you're testing a directional hypothesis, the p-value that is given in the table can sometimes if you stick with that and you compare that against the alpha level, then you can underpower your test and fail to reject the null when you should be rejecting the null. So in this particular case right here, we are going to reject the null hypothesis, and basically we can say that the mean at time 1 for anxiety is significantly greater than the mean at time 2. Let's say, for argument's sake, that let's say I was looking at changes in anxiety scores between time 1 and time 2, and I was looking at the effects of some kind of treatment in terms of increasing anxiety. It would probably be unethical, but let's just say I was doing that just for argument's sake. So in that particular case, my research hypothesis would actually be mu1 minus mu2 is less than 0, because essentially the time 1 score should be lower than the times 2 scores. So if I had the same, let's just say that this data was applied to that research context, and so these are the means that I obtain, I would still have the same p-value, but so the thing is that a lot of times people get into trouble looking at just the p-value and they forget about the mean difference itself. The p-value is agnostic to the direction of the mean difference, so it's not concerned with the direction of difference. So if you stick with just looking at the p-value, then you may end up rejecting the null, when in fact you ought to be failing to reject the null, because we had specified a directional hypothesis. The mean difference was contrary to the direction that you had hypothesized. So even if the p-value was less than the alpha level that you had set, if the mean difference is not in the direction that was hypothesized, then you cannot reject the null hypothesis. So that's just a little something to kind of keep in mind. Another thing to kind of note is that when it comes to the paired samples t-test, it assumes that the difference scores, or if I was to take time 1 minus time 2 scores, the difference scores is normally distributed. So we can assess that assumption if we create a new variable in SPSS. I'm just going to call it diff. So the target variable, you can give any name, but basically you just take this variable right here, subtract this variable right here, and it gives you a new variable in your data set. Oops, keep going back to that other data set. So and so keep in mind, really quickly, I want to note that the measures that for some odd reason were defaulting as nominal, but basically the computations didn't really matter in this particular case. The computations will be carried out regardless of how you'd actually scale the original variables. It would be using the original, basically the same formulas. But anyway, just to be consistent with what we would want, I just gone ahead and just called these scale variables, which is that they're an interval ratio level of measurement. So at any rate, we have difference as our difference scores, which is just anxiety 1 minus anxiety at time 2. So we can evaluate the normality assumption using the explore function. If we go under explore dependent list, we can click on statistics. If I want to explore for possible outliers, I can click on this and continue. Under plots, I can ask for a histogram and normal probability plots and tests, and then OK. And so basically, I can look at the skewness and kurtosis statistics. Skewness and kurtosis are two dimensions related to the distribution that have a bearing on whether the distribution is normal. So conventionally, skewness values that that fall between -1 and +1 suggest that your data is not strongly skewed. So values that are closer to 0 actually indicate that you have less of a skew. And there's no perfect normal distribution with data. So the closer you are to 0, the better. And so one threshold for judging more extreme levels of skewness is a value that is greater than 1, or a value that is less than -1. So in this particular case right here, there appears to be some positive skew in the data, and it certainly exceeds this threshold here. In terms of kurtosis, we can utilize sort of a similar scale. 0 would be consistent with normality, which is, in terms of kurtosis, would be a mesokurtic distribution. A value that is greater than +1 would indicate that you have more extreme levels of kurtosis. A value that is less than -1 would indicate also more extreme levels of kurtosis. Positive values are indicating more of a leptokurtic distribution. Negative values are indicating more of a platykurtic distribution. So in terms of kurtosis dimension, that seems to be less of a problem. So it looks like we have more of a little bit of a positively skewed distribution here. So we can also, those are descriptive indices that pertain to your normality judgment. You can also look at the Shapiro-Wilk and Kolmogorov-Smirnov tests. I generally go with the Shapiro-Wilk. And this is a significance test to test whether your data is departing significantly from normality. So in this particular case right here, we see that our basically this is a p-value, and you can compare this against your alpha level, and if p is less than or equal to, say, some low alpha level of 0.05 or whatever, then you would reject the null. And rejecting the null in this context is actually a bad thing. That actually would mean that that your data is departing significantly from normality. So in this particular data set right here, those difference scores are departing significantly from normality. So we can, the downside of these tests, though, keep in mind, is that they're affected by sample size, which is a factor that impacts any inferential test, like the paired samples t-test or the independent samples t-test and so forth. So if you happen to have a larger sample size, that can yield statistical significance, even if you have minor departures from normality on the difference variable. Whereas if you have smaller sample size and you find no significance, it could reflect, basically you may not have enough power in your test to be able to detect even a more substantial departure from normality. But in this case, we actually had a pretty small sample size, and we found a significant difference. So that would certainly be consistent with our assessment above, looking at those descriptives. And then here's our histogram right here. And you can see you see the skew as it appears, and you can see that it just does not look very normal. So there you go. Up here in the extreme values, these are the extreme values for your difference variables. And so these are, when you're looking at the extreme values, the highest and lowest, these are giving you possible cases that might be possible outliers in your data set. This does not mean that they are outliers. You have to do a little bit more investigation in order to determine if you have any outlying cases. So these are just the cases that have the most extreme values, and really none of them are particularly extreme. Probably the most extreme values are for cases 7 and 8 in the data set, because for those difference values that you had 5s for those cases. But one way of further assessing for possible outliers is to generate z-scores on the difference variable. And so we can click on this right here and click on OK, and essentially look at the z-score values. And so you'd be looking for z-scores that would fall above +2 or below -2. And so we don't have any of that sort of situation occurring here. And then finally, another way of looking at possible outliers is to look at the box plot, or box and whisker plot, and you can kind of look, basically in this particular case right here, these values are sort of departing from everything else. So at any rate, this was a very small data set, so the box plot is a little weirder given that particular situation. But if you happen to have a violation of the normality assumption, then what you could do instead of running the paired samples t-test, you have a couple of options. If you go to non-parametric tests, to legacy dialogues, and then down to 2 related samples, because we have 2 related samples, obviously, we can ask for, we can move our pre-test and post-test scores over here, and there are a couple of options in terms of tests that we could run. We could run the Wilcoxon sign ranks test, or just the sign test. So these are 2 different tests. We can click on OK. So the Wilcoxon sign ranks test, basically we're testing whether there is a significant difference in the sum of ranks in terms of positive and negative. And so the basic idea behind this is that if we take the differences in raw scores on anxiety, and what we're looking for are the amount of positive and negative ranks associated with those differences. So essentially, in this particular case, the negative ranks, the sum of those negative ranks was 45, meaning that really we had most, our scores at post-test were less than those at pre-test. And by the same token, you can see with the positive ranks, it happens to be actually 0 in this case. So in our data set, it actually turned out that it was pretty much uniform change in terms of the sign of the difference, except for one case where there was actually a tie. There was basically a person scored, I believe, at 3 at time 1 and time 2. So there was no difference there, and so that was the tie that we see right here. If it was the case where the converse was true, let's say that we had 45 for the positive ranks and let's say 20 for the negative ranks or something like that. Essentially, then what that would kind of indicate is that basically our scores would actually be increasing from time 1 to time 2. So we have a z-test right here, and so this is the z-value, and then we have an asymptotic significance test that's using the z-distribution. So we can see it's 0.007, which would be less than 0.05. So that would indicate to us that we have a significant decrease in anxiety scores from time 1 to time 2, and that's also reflected in the fact that we have this negative value for the z-value. If the z-value had been positive, then that would indicate to us that we would have a significant positive increase in anxiety scores between time 1 and time 2. And thankfully, that is not the case in our current study. We also have the sign test, which is very similar to the Wilcoxon sign ranks test, except that we're not using ranks for your dependent variable. We're just looking at the signs for the changes or the difference, the signs for the differences between time 1 and time 2. And so this is actually an exact test as opposed to an asymptotic significance test. And so this actually makes this probably a little bit more useful when we're dealing with smaller sample data as opposed to the asymptotic test that we have up here. So at any rate, we see that there is a significant difference in the positive and negative difference scores that's associated with the time 1 and time 2 changes. So to give you just one smaller example, I've kind of modified a couple of variables where actually now if we compute the difference scores, we'll actually see in our data set, you can see a couple of negative differences here. So if we go back and we rerun those non-parametric tests for this particular data set, you can see the sum of ranks a little bit more clearly. So we had 32 for the sum of negative ranks and 13 for the sum of positive ranks, which again, the time 1 anxiety scores are higher than the time 2, and so that's what's producing the higher sum of negative ranks here as opposed to the sum of positive ranks. You can see though in this case the difference in scores between time 1 and time 2 is not statistically significant. And then if we look at the exact test results, you can see that there was no significant difference between time points as well. So one other kind of illustration I wanted to bring up, with paired samples tests, it's not only utilized in the context where you have data that comes from like a time data where you're looking at change over time, but you could also look at differences. Anything that has any research design that has a paired sample, like let's say I'm sampling pairs of siblings or sibling pairs from two children families, and I want to look at differences in perspective taking between older and younger siblings in those families. So each case would actually represent a family as opposed to an individual. This would be the older sibling's score on perspective taking and the younger sibling's score on perspective taking. So in this case, we would have paired samples because they're coming from the same family. So we could carry out the same exact test that we just did with respect to the time data and have no problem. So at any rate, that concludes this discussion of paired samples t-tests and some alternatives to those t-tests as well.